It's easy to measure how much oxygen is in the air that a patient is breathing, and it's easy to measure how much oxygen is in the blood, but it's really hard to measure how much is in the alveolus. So instead of measuring it, we calculate it using the alveolar gas equation. And it's a simple idea. Basically, the amount of oxygen, or the partial pressure of oxygen in the alveolus, is going to be how much has gone into the alveolus by breathing it in, take away how much is consumed or removed. There's only one way to get oxygen into an alveolus, and that's to breathe it in, and that's what this term talks about. There are two ways that oxygen can leave an alveolus. It can either be consumed into the blood, or it can be exhaled again, and that's what this term is all about, and we'll break it down. But first of all, there are some assumptions we need to make. The first is that the patient is at steady state, so there is no accumulation or loss of CO2 or oxygen. The second assumption is that all the gases obey Dalton's law of partial pressures, which means that if you've got a mixture of gases, they all contribute to partial pressure and they all add up to the overall pressure of the whole mixture, or atmospheric pressure. We also assume there is no rebreathing of CO2, so once the patient has exhaled some CO2, they don't rebreathe it back in again. We also assume that CO2 diffuses really, really quickly from the blood to the lungs, and I'll explain why this is really important in a minute. Finally, we assume that the upper airway humidifies and warms the incoming gas to body temperature and full saturation. Starting with CO2, it's produced by the cells during aerobic respiration at around 200 mils per minute in the average adult. It's carted off in the blood to the lungs where it is then exhaled, and because we've said we're not rebreathing, we assume all of it is being exhaled. The patient is at steady state, so there can't be any accumulation or loss of CO2, so we must have all of that CO2 being exhaled by the lungs. This is how we get the equation VCO2, or the production of CO2, is equal to the expired concentration of CO2 times by minute ventilation. This basically means that's how quickly we're producing it, that's the concentration in the alveolus, and that's how quickly we're breathing it out. By definition, those two must equal each other if this statement is true. Now, oxygen gets inhaled into the alveolus, but it has two ways that it can leave. It can either be absorbed into the blood, or it can be exhaled again. So we have to factor in both of those pathways to our equation. So the VO2 is the consumption of oxygen, and it has to equal your minute ventilation times by the difference in how much you're taking in and how much you're exhaling. So we've got an equation for CO2 and we've got an equation for O2. Now we need to know how the O2 and the CO2 relate to each other so that we can work out how much oxygen is being swapped for CO2 in metabolism. And this is where we have the concept of R, or our respiratory quotient. The respiratory quotient is the ratio of CO2 production to oxygen consumption. If you metabolize a carbohydrate, the molecular formula is usually something like CHO, and you just have lots and lots of these together. There's oxygen already embedded in the molecule, which means you need less oxygen to produce each CO2 molecule. But fats are often mostly CHs, hydrocarbons, with much less oxygen, so they need more oxygen to produce a molecule of CO2. As a result, the ratio for metabolizing carbohydrates is 1, and the ratio for metabolizing fat is about 0.7. So we take an average of this for the normal person, and we say that their respiratory quotient is about 0.8. If we then just combine the two equations, we end up with this, which we can rearrange to give us the basics of the alveolar gas equation. And this looks like our original term, where the fraction of oxygen in our alveolus is how much we've inhaled, take away how much is swapped for CO2 or is exhaled. This bit here is where we care about Dalton's law, because it basically says the percentage concentration can be exchanged in our equation for the partial pressure, which is how we get from F to P. So instead of just saying the fraction of alveolar oxygen, we now just say the partial pressure, because Dalton's law allows us to convert. So we say PiO2 minus Pa CO2 over R, and then this point here, that's partial pressure of alveolar CO2, but earlier we said we assume that CO2 can diffuse really, really quickly. The reason we want to do that is it allows us to use P a, little a, which is the arterial CO2 partial pressure, which we can measure much more easily. So that's how we end up with PA with a little a in the final equation. If we go back to the original equation, we just need to look at this term quickly. If you look here, the pressure, or the partial pressure of oxygen that you inhale is going to be the percentage oxygen in the air times by atmospheric pressure. This is why you have to hyperventilate at high altitudes, because while you're still breathing 21% oxygen, atmospheric pressure is much lower. So to get the same level of oxygen in your body, you need to ventilate much harder. We mentioned earlier that the body humidifies and warms the air as it enters the trachea. This water vapor can't hold any oxygen, but it occupies a volume, which means that the gas you are inhaling can't hold as much oxygen as if it were pure dry air. And we have to account for this in our equation. So that's how we end up with your PiO2 actually being FiO2 times by atmospheric pressure minus the pressure of that water vapor that can't hold any oxygen. And that is how you get that first term in the equation. It's really complex as an idea, but if you go over it a few times, it does start to make sense. But the overall reason we have the equation is we want to know the amount of oxygen in the alveolus, and the only way we can really calculate that is by working out how much we're putting in and then working out how much we're taking away. If you want to know more about the alveolar gas equation, we've got a full article about it on anesthesia.com.